All right, let's look at rates of change and tangents to the curve. So we've talked about that calculus is the study of change, and we want to look at the speed of an object and direction of motion at any instant. Like, for example, how does the speed of an object change as a function of time? So this is going to give us the beginning of our concept of a limit, and then we'll grow from that, as well as we might want to find velocity of a moving object and the tangent to the curve, and we'll talk about what that is. So we're going to develop this limit intuitively and formally first, and then we'll dig deeper into it, and we'll also use limits to describe the way the function varies, such as continuously, small changes in x, produce only small changes in f of x, jumps in the function, increase, decrease without bound. Galileo's free-fall law, very famous law that he discovered that an object dropped from rest near the surface of the earth and allowed to fall freely will fall a distance proportional to the square of the time it has been falling. So in other words, we're just saying only gravity's acting. So if I let y equal the distance falling in feet after t seconds, then Galileo came up with this equation that said the distance falling equals this constant of proportionality times the number of seconds squared. Now, because Galileo, being who Galileo is going to use metric units, if you research this, you might actually see it written in metric units. So it's the same equation, it's just in this case, instead of my y being in feet, my y is going to be in meters. You committed a murder. You killed me. The cops have you surrounded at the top of Towers of America, 750 feet up. You dropped the murder weapon, which was a toaster, can you believe you killed me with a toaster, over the side. How could we look at the average speed of this toaster? Think of in general, how do you find average speed? When you go on a trip and somebody says, what was your average speed? How do you normally answer that? I mean, typically we say in miles per hour, but think of the miles is my distance, and then the per hour, that's my time. So what we're really looking at is the change in distance over the change in time, our length of our time interval. So an object's average speed, in this case the toaster, during an interval of time is found by dividing the distance covered by the time elapsed. So the change in the distance over the change in the time. Once again, you drop the toaster from the top of the tower. I want to find the average speed the toaster is traveling the first 2 seconds of the fall. In other words, the first 2 seconds would be from right away, time equals 0, to time equals 2 seconds. So if we go in back to our definition, so let's just start it by saying this is to find the average speed is the change in distance over the change in time. And we can shortcut write that as the change in y, because we said y gives us our distance, over the change in t. Remember we said those little delta symbols mean the change, so the change in y over the change in t. Well, the average rate of change formula says that, well, my change in y is my change in my function, so that would be my change in t sub 1 minus f of t sub 0. So in other words, whenever you look at from 0 to 2 seconds, how you find that change is you start with the larger value, and that's why that's my t sub 1, and then you subtract the smaller value, my t sub 0. And then my change in my time then would be t sub 1 minus t sub 0. So hopefully that kind of sort of looks familiar to you, because this is the average rate of change formula that I told you is very, 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 very important, because we're going to use this a lot actually in here, and so you certainly need to know it. So how do we use it? Well, we take our equation, our function in this case, because what we're really saying is that the change in my distance traveled, is a function of t. So I'm going to plug in my t sub 1, which is going to be 2, and my t sub 0, which is going to be 0, into my function. So in other words, I have 16 t, which is 2 squared, minus 16 t, which is 0 squared, all divided by my change in my time, which is 2 minus 0. So that's all I've done, is I've used my y equals 16t squared, my function here, and I did it for 2 seconds and 1 second to get my change in distance, and then I did 2 minus 0 to get my change in time. So multiplying that out, I do 2 squared, which is 4. 2 minus 0's 2. That gives me 64 over 2, which gives me 32. Now, an average rate of change, remember, a slope is an average rate of change, and when you were finding slopes, we tended to like to write them as a fraction, because then I can go back to my original fraction and say, well, what is the 32? It's the change in distance. Well, what is distance? It's feet. And then what is the 1? That's my change in time. Well, my time is in seconds. So this is saying my average rate of change, that the toaster is falling from 0 to 2 seconds, is 32 feet per 1 second. All right, back to this toaster you dropped from the top of the Tower of Americas. What if we wanted to now know what the average speed the toaster is traveling during the 1 second interval between second 1 and second 2? In other words, between 1 and 2 seconds, now what's the average speed that this toaster is traveling? Well, we go back to our average rate of change, which said I'm going to take my change in my distance over my change in time. Now I'm interested between 1 and 2 seconds. So my 2 becomes my t1, and my 1 becomes my t sub 0. So I go back to my equation, 16 2 squared minus 16 1 squared, all over 2 minus 1. So that gives me 64 minus 16 over 1, which equals 48 over 1, and we know this is in feet per second. You drop the toaster from the top of the tower, but now I want to know the average speed the toaster is traveling between 1 and 1.1 second. So I still go through my average rate of change. I go through my change in y over my change in t, but now I'm interested between 1 and 1.1 second. So I plug everything in, 16 times 1.1 squared minus 16 times 1 squared, all over 1.1 minus 1. I get 3.36 over 0.1, which actually gives me 33.6 feet per second. Hopefully you see where this is going. I want to know the average speed the toaster is traveling during any time. I don't want a time interval anymore. I want to know at exactly 1 second or at exactly 2 seconds. So how could we do that? Well, if I want to determine the speed at any second, so of time t sub 0, instead of within an interval, if you notice what I was doing, I was letting my intervals get smaller and smaller. I started from 0 to 2, and then I said, how about from 1 to 2? How about from 1 to 1.1? And so I let my intervals get smaller. So I start out with some interval, maybe from 1 to 2, whatever it is. And notice here is my average rate of change. So nothing has changed with my function here. And let's call this distance from my first interval to my second interval h. Let's just call that h. Then notice if I wanted to find this distance, my t sub 1 that it used to be becomes the distance t sub 0 plus h. How do you find the distance? You subtract, so t sub 0 plus h minus t sub 0. Notice the t sub 0's cancel and I just get h. So I replaced my denominator with h, and I've also replaced my t sub 1 with t sub 0 plus h. So I'm just rewriting this, calling it different variables. All right, so my key here is I'm going to let the time intervals get smaller and smaller and smaller and smaller. So what you're seeing happening is I'm basically letting this h, this distance, approach 0. I'm letting it get small, 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 and so on. Well, you might say, well, if you wanted exactly t sub 0, you would make h equal 0. Well, you can't let h equal 0, right? Because if h equals 0, bad things happen. Remember all Homeland Security and stuff, you cannot divide by 0. So how small can you make that? In other words, we're saying as h approaches 0. Well, that distance is actually up to you, what you are measuring. Okay, maybe you're measuring with a ruler that only does centimeters, and you can't get anything more precise. Maybe you have a more precise measuring tool, and so you can get something that would be as small, this distance here, as you can make it. All right, let's see what's going on here as we're making this h, our time interval, smaller and smaller. So in other words, I'm interested in the time at exactly 1 second. Well, I could go from 1 to 2 seconds, that would be a time interval of 1, or I could go to 1 to 1.1, which is what we did, and we got the 33.6. I could even make that h smaller. I can make it 1 to 1.01, and so on. Well, if you notice what's happening as my h is approaching 0, this value is approaching what we call a limiting value. And if you dump the decimals, you can see it appears that my average speed is approaching 32. Okay, so my 32 feet per second, because as I'm letting h get smaller and smaller and smaller, I'm letting it approach 0, then the value of my function is also approaching a value, and that's what we call the limiting value. So this suggests the toaster is falling at a speed of 32 feet per second at exactly 1 second. And that's the important part, is now I'm going to say at exactly, I don't care between 1 and 2 seconds or between 1 and 1.1 seconds. I want to know at exactly 1 second how fast that toaster is falling. So we just came up with, and we said at exactly 1 second, the toaster was falling 32 feet per second. We could actually prove that algebraically. So we start with our average rate of change. And notice my t sub 0, my exact, what I'm looking for exactly is 1. Okay, so that's my exact piece right there. So what I end up doing everywhere in this average rate of change that you see a t sub 0, I put in a 1. I'm also plugging this back into my function. Remember, this is my f of t. So where I see a t, I'm going to actually plug in 1 plus h. So let's do an extra step here. I'm going to just show you that I'm replacing my t sub 0 with a 1. That's all I did. Now I'm going to take and replace my t with a 1 plus h and then my t with a 1. So this is going to become 16. Where I see a t, I put 1 plus h. It's squared, so that's my 16t squared. Minus, now my f of 1, which is going to be 16 times 1 squared, all over h. Well, let's use our algebra skills that we know. This piece is FOIL. This is 1 plus h times 1 plus h, where you're FOILing out the first term, the outer terms, the inside terms, and the last term. And so the 16's out front. If you remember the little trick, when you multiply a square, you square the first term, so 1 squared is 1. You take 2 times these two terms, so 2 times 1 times h, 2h, and then you square the last term. If you don't remember that, then you go through FOIL. That's what I did, is it's a shortcut way of FOILing. And then minus 16 all over h. So this now gives me, I'm going to distribute the 16 to everything inside the parentheses. So I get 16 plus 32h plus 16h squared, and then I still have that minus 16 sticking out there. And so now at this point, what I can do is I can take and cancel my 16s, and I'm left with 32h plus 16h squared over h. On the top, I'm going to factor out an h. So that leaves me h times 32, because I factored out an h, plus 16, and I had an h left over, and an h on the bottom. So now these h's cancel, and I get 32 plus 16h. Well, remember our h was that error. That was that distance that we wanted to let it approach 0. So as h is approaching 0, then this becomes 32 plus 16 times 0, which gives me my 32 feet per second, that limiting value. So that was showing us, this shows us algebraically that what we were doing by plugging in smaller and smaller and smaller and smaller values, that our limiting value at exactly 1 second is approaching 32 feet per second. All right, we went through at exactly 1 second. Well, you can do the same thing at exactly 2 seconds. You can go from 2 to 3, from 2 to 2.1, and you can let h approach 0, and you will see that your value is approaching 64. So in other words, this is saying that the toaster is traveling at exactly 2 seconds, 64 feet per second. So you can use the same approach that we just did, and you can solve it the same way algebraically by plugging in 2's, and then you would see you would get your 64. So let's say we have just an arbitrary function, y equals f of x, and we want to calculate the average rate of change of y with respect to x over this interval, x1, x2. So to do that, what we're going to do is just set up our definition. Our average rate of change, once again, is the change in y over the change in x. We say that we had a function, and here is our interval. So this becomes my f of x2 minus f of x1 all over x2 minus x1. And we said that we're going to let x2 equal x1 plus that distance. Okay, remember we started out with x1, x2, and then we said let h be that distance. So now x2 becomes x1 plus that distance. And then of course on the bottom we're saying that let my x2 minus x1 equal that distance h. So we can just simply rewrite this now as f of any function plus h minus f of x sub 1 all over h, where of course h cannot equal 0. And this is our definition of the average rate of change. Let's look at the geometric definition of the average rate of change. So if I have my graph here, and then in my graph, get some different colors going on, I have some function, say it looks like that, and I can start labeling some points. So let's say I have, this is my x sub 1, so that point right there, we'll call it P, would be x sub 1 comma our y value, which is our function evaluated at x sub 1. So that would be that point. Then I can come out here and get an x sub 2, which we said we're calling x sub 1 plus h. And I can get another point here, let's call it Q, which would be my x value would be x sub 1 plus h, comma, my y value, which would be f of x sub 1 plus h. So that's my y value. So all of this is my ordered pair, my x comma y. And once again, we said that this change in x equals h. So that's just how we defined it. Now I can come back and let's say if I connected these dots, let's see if I can do it, with a straight line. It's almost straight, huh? Pretend that was a straight line. You laugh, but you try to do this with a little mouse pad thing. So if I connected these, I'm touching the function in two places. This is called a secant line. So my secant line is a line joining 2 points of a curve. Just a little definition there. So that's my secant line. If I want to find that slope of this line, once again pretending it's straight, how do we find the slope? Well, the slope of the secant line would be my change in my y over my change in my x's. So again would be my change in my y over my change in my x. So this gives me, geometrically, it makes sense that if I have this secant line, this gives me the average rate of change over from x1 to x1 plus h. But what we want to ultimately do is to see what happens when we start making this distance, our h, smaller and smaller and smaller. Meaning, if I move the point Q a little closer, now my line becomes that. I move it a little closer, now my line becomes that, to the point that I want to let my h approach 0, and you'll see it written like this with the arrow. As h is approaching 0, this distance is getting smaller and smaller and smaller. I'm going to get to a point where I'm only touching p, that point of my function, in that one place. And that's what we're going to call our tangent line. So we're going to allow this Q to get closer and closer and closer to where we're only touching P in that one spot. And so a slope of a line is the rate at which the line rises or falls. A slope of a curve is the slope of the tangent line to the curve at a particular point. And this is showing what I was trying to show with not so nice straight lines, is that I'm going to start out at another point Q, and I'm going to let this distance I'm going to get closer and closer and closer, and notice the slopes of my tangent lines are changing. And so ultimately what I want to say is the distance from P to Q, that's my h, is ultimately I'm letting my h approach 0, so I'm only touching P on that tangent on one place on the curve. All right, let's find the slope of the parabola y equals x squared at this particular point. So basically what we're doing, and we all know what x squared looks like. Let's get another color going on here. We know our parabola looks like this. That's our y equals x squared. And what I want to do is I have this point 2, 4. And I want to begin, I say we begin with this secant line where my second point is somewhere here, and we'll call that distance 2 plus h. But I want to know at exactly the point where x equals 2. So what I'm ultimately doing is I'm shrinking this. I'm letting my h approach 0. So to find this secant slope, so my secant slope, which again would be the slope if I drew a line between these 2 points, so that becomes my secant line. That's my secant line. And we already said we know how to find the slope of the secant line. So I'm going to take my function here. My x is going to be my 2 plus h, and it's squared, minus my second point, which is 2, and it's squared, all over h. Let's just do the algebra stuff. And once again, this piece right here is FOIL. I'm going to do that shortcut that I mentioned that says you square the first one. 2 squared is 4. You take 2 times these two terms, so 2 times 2 times h, which gives me 4h, and then you square the last term, which is h squared, and then 2 squared, which is 4, all over h. You can see those cancel, and I can even factor out an h out front to get 4 plus h all over h. My h's cancel, so I end up with this 4 plus h. Well, remember we're saying that as my second point, and let's call that point Q again, as Q approaches P, which is my first point, along the curve, I'm staying on that curve, then my h is approaching 0. So then 4 plus h would simply be 4 plus 0, which gives me 4, which is my secant slope. So that would be my secant slope. Looking at this a little more nicer, okay, so you can see here's my x squared. I started out here with q, and I'm bringing this point down this curve closer and closer and closer and closer till I'm letting my change in x, my h distance here, approach 0. And as it approaches 0, at exactly that point, I'm tangent, that's this pinkish line, I'm tangent at the point 2, 4, and I get my slope of my tangent line, which is 4. So now what I could do is I can actually find an equation for the tangent to the parabola. So if you remember, well, first we had my tangent slope was 4. I have a point here, 2, 4. In algebra, you learned if you had a slope and you had a point, you could use the point slope formula, which said y minus y1 equals m times x minus x1. I start plugging things in. My y1 is 4. My slope is 4. And then my x1 is 2. Distribute out this 4, so I get 4x minus 8. And then add 4 to both sides, and I get my equation of my tangent line. So this is the equation of the tangent line at that point on this curve. So what we've found out is our slope of our secant line is our average rate of change, where the slope of our tangent line is at exactly our instantaneous rate of change. And that's the big key in this section, is that if we're looking at average rate of change, that's where we have the 2 points on our curve. We connect the 2 points, we get our secant line. As we bring that second point closer and closer and closer to the first one, we let our distance approach 0, then we're tangent on the curve, and we get our slope of our tangent line, which is instantaneous rate of change. Let's look at a volume of a balloon example using the average rate of change. So the volume of a spherical balloon changes with the radius. I want to know at what rate does the volume change with respect to the radius when r equals 2 feet. Well, the first thing you have to remember is what's the formula for the volume of a sphere, okay? That's the 4/3 times pi times the radius cubed. And so this is what I'm going to plug into my average rate of change formula. So my average rate of change says I'm looking at the radius plus that distance minus the radius over the distance. And I want to look at this as my distance, my h, is approaching 0. So once again, here's my volume formula. I said the radius is 2 feet. So I plug in 4/3 times pi times my radius, which in this case is 2 plus h, and don't forget that's cubed, minus, I simply take my volume, and where I see radius, I plug in 2. Now it becomes an algebra problem. There's a little shortcut if you remember, but when you cube something, this is 2 plus h times 2 plus h, that's FOIL, and then also times 2 plus h. But this little formula is nice that says to square the first one, so 2 cubed, 8, take 3 times the 2 squared. So 3 times 2 squared would be 3 times 4, which would give me my 12. And then I write my h, which is my b. And then 3 times 2, which would be 6, times now my b is squared, so that's my h. And then I cubed the last one. So that's how I got this. So this is my 2 plus h cubed, my 8 plus 12h plus 6h squared plus h cubed. Only other thing I did here is I went ahead and I cubed the 2. I'm going to distribute the 4/3 pi times 8, 32 over 3 pi. All right, one of the big keys to understanding that I'm telling you when you're finding instantaneous rate of change that you're finding the slope. So if that's true, if I have a linear equation, a line, we remember that whole y equals mx plus b. If I'm telling you that this formula, that's h minus f of x1 all over h, is giving me the slope at exactly that point, well, a linear equation, the slope's constant, and the slope is always 3. If you believe me, then when I plug everything in, I better get 3 for my answer. So let's start plugging everything in. I have 3. Where I see an x, I plug in my x plus h. Well, I already know what my x is. My x is 2, and there's my plus h minus 2. So in other words, my x1s here are 2. And then my second set is where I see an x. I plug in a 2, and then all over h. So away I go distributing. 3 times 2 is 6, plus 3 times h is 3h, minus that 2. This is 3 times 2, which is 6, and 6 minus 2, which gives me 4. Okay, so this is 6 minus 2, which gives me 4, but don't lose that negative sign, so that's negative 4 all over h. Well, 6 minus 2 is 4, and that would cancel with that 4. So I'm left with 3h over h. How nicely the h's cancel, and looky there. I said that this is the formula for the slope, and it matches the linear, so now that should convince you that that's all you're doing is just simply finding slopes.